Okay, 10.4 is going to be a bit of a doozy. This is a big section of the book in the sense that this really influences a lot of things that come later on. What we're going to be learning here is something that's complicated enough that it's going to take two sections. We're going to do some of it today with 10.4, and then we're also going to continue this topic in 10.5 for the really tough cases. It at first doesn't look all that different from section 10.3. 10.3 had a rule for multiplication that said you could put together two roots as one big root. And the rule for division is essentially the same rule. If you're dividing a couple of roots, you can make one big root out of the two. If you're thinking back to 10.3, you'll remember that we used the rule primarily backwards to break roots up for simplification. So you might think that what we're going to do right now is similar, that we're going to use the rule backwards for simplifying by breaking up numerators and denominators or something like that. And unfortunately, nope, that's not what we're going to be doing. We're going to be doing something very different. We're going to be learning about a process called rationalizing. And here's what rationalizing is about. Let me show you an example done two different ways. Let's say we have as our starting point the fraction square root of 7 divided by square root of 3. That has two square roots in it. And yes, you could make one big root, but it would be the square root of 7/3, and that's even worse. Square root of a fraction, I'm sure your mind runs in a panic when you try to think about that. Instead, what we're going to do is we're going to take these fractions and multiply top and bottom like you normally do with fractions by the same thing. You know, you use this when you're trying to get a common denominator. Multiply the top and bottom by the same thing. Now you got two choices. You can multiply top and bottom by square root of 7, or you could multiply top and bottom by square root of 3, and depending on which of those two things you pick, you end up with a nice root either in the numerator or a nice root in the denominator, which means when you're done, you have an expression, one way or the other, that only has a single root in it rather than two roots. So these answers we have here, they are simpler than the thing we started with, because they don't have as many roots. But we don't like having two choices to pick from. I mean, there should be one simplest form, not two simplest forms, plural. So the one that's decided to be the simplest form is this one. The one at the top is a simpler form than where we started, but it's not the simplest form. So this one is what we call simplest form. And to remember to do this, the phrase that we want you to remember is rationalize the denominator. The idea is roots that don't simplify are irrational numbers, and nice whole numbers like that are rational numbers, so we're trying to make the denominator rational. It all has to do with the actual process of division that you would have to go through if you divided with pencil and paper. The bottom problem is a lot easier to do the division than the top one, so that's why that was chosen as simplest form back in the day. So let's practice this basic idea before we do a couple of tough examples. The basic idea is to take something like this and multiply top and bottom by whatever it takes to simplify the denominator. And the problem here, this is the thing that students really have trouble with. The problem here is the initial problems like this one, they're really, really simple. Here, your denominator technically is square root of 25, but you and I both know what the square root of 25 is. That's just 5. And that's the simplest form for that. And this next one, same basic idea. And it's so easy in this case that your mind can't help but invent a shortcut. And you're going to probably describe this in words or something inside your mind, and what you're going to tell yourself is multiply top and bottom by the denominator. And that's not the rule. That's really not the rule. That rule works just fine for these simple ones, don't get me wrong. This is a very simple way to do these simple problems. Multiply top and bottom by the denominator will work at first. And that's almost the problem is, at first you think you've discovered something. You're like, hey, look, I found this cool shortcut. Just multiply top and bottom by the denominator. It always works out beautifully. Sometimes you'll make mistakes at the end because you'll forget to do regular old-fashioned elementary school reducing, like 6 and 2. Can't you reduce that? Yeah, of course you can reduce that. So the simplest form is 3 root 2 for that one. But this simple rule for just multiplying top and bottom by the denominator, that only works when your denominator is a single, simple square root. If you make things even a little bit more complicated, that rule doesn't work anymore. So let me immediately go to the trickier cases, because I don't want you to build that bad habit that only works in the easy cases. I want you to be able to do the tough cases too. In fact, let me show you why that supposed shortcut doesn't work. If you were to just robotically mimic what I did a second ago and simply multiply top and bottom by the denominator, what you would get here is a denominator that is the cube root of 4. It's not the square root of 4, the cube root of 4. And the cube root of 4, that's not a particularly nice number. It's still a grab a calculator problem, gives you some messy decimal. That is not going to clean up and simplify. This part here is not good news. Frowny face. Okay? So I'm going to show you a total of 3 different techniques for handling this type of situation. The first technique is to remember what you're trying to accomplish. You're trying to be able to get a root in the denominator that will come out nice. So what I'd like to be able to do here is, in a second, the number that's about to go in there, I want that number to be something I can do the cube root of. Not 4. 4 was a bad idea. 4 doesn't go anywhere. But I want this number here to be something nice. So you just have to be familiar with perfect cubes. And you have to figure out a perfect cube that you can hit, that you can target in this case. So in this case, if I multiply by the right thing, these two together will multiply, and I promise you there's a way to do this, to get the cube root of 8. And then in a second, the cube root of 8 will come out to be 2. So then the tricky part is, what magic number has to be there, 2 times something, to give me 8? And I bet it's not as complicated as I'm making it sound. It's actually pretty easy. Isn't it 4? 2 times 4 gives you 8. So multiply top and bottom not by the same thing as the denominator, but multiply top and bottom by whatever it takes to make the denominator come out nice. Now in this case, the numerator doesn't simplify any, but that's typical with a rationalize the denominator problem. Usually your numerator has a root in it and your denominator doesn't. Some people don't particularly like that technique, so let me show you an alternative technique. The alternative technique is to realize, since this is a cube root, we need to make a cube. Cube root and cube will cancel. So in order to make a cube, I have to have 3 identical things multiplied together. Something times itself 3 times makes a perfect cube, doesn't it, right? So here what I would have is I would have the cube root of 2 times itself 3 times, and there's that root, and exponent canceling business. Cube root cubed cancels to 2. Of course, if you multiply the denominator by some kind of a thing, you're going to have to multiply the numerator by the same kind of thing. And here, those two together make the cube root of 4, just like we had a second ago. So depending on how your mind works, you might like technique number 1, or you might like technique number 2, and it's really different for different people. There isn't really a better technique and a worse technique. Neither one of those techniques works particularly well when you get to tough problems, though. They're okay for sort of medium-level problems, but when you get to tough problems, like this one here, you're going to need a third technique. Really, it's almost impossible to use technique 1 or 2 effectively. You end up having to use very large numbers that are way beyond your ability to think of perfect cubes. Like, anybody know what, like, 13 cubed is. It's way too big. You're not going to be running into numbers that large conveniently. And technique number 3 is a way to avoid that. In technique number 3, what we do is we borrow an idea from when we were working with variables, and we take the 12 and we factor it out into as many simple pieces as we can. So we're going to factor it into 2 times 2 times 3. That's prime factorization. 12 breaks up as 2 times 2 times 3. And then I'm going to multiply the top and bottom by some kind of a cube root. And when I'm done, what I would like to have is in this denominator here, I'd like everything I write to have an exponent of 3. Because if I'm talking a cube root, I want cubes and cube roots to cancel each other. So think of each prime separately. Like think about the 2's, focus on just the 2's and say, okay, I want to end up with 2 to the 3rd. Currently, I have 2 to the 2nd. What would it take to make sure that I end up with 2 to the 3rd? Well, I would need another 2. 2 times 2 times 2. 3 2's multiplied together would make 2 cubed. Then focus on the next prime. Think about 3. I want to end up with 3 to the 3rd. Currently, I have a single 3. So to get to 3 to the 3rd, I'm going to need 2 more 3's. 3 times 3 squared will give me 3 to the 3rd. And then once you've figured out what to multiply by, the simplifying of that result is really easy. 2 to the 3rd, cube root makes 2. 3 to the 3rd, cube root makes 3. And of course, 2 times 3 makes 6 for our denominator. Our numerator is kind of low-tech. You wish it was something fancier, but it's not. You just sort of do the arithmetic. 3 squared is 9. 9 times 2 is 18. We end up with 5 cube root of 18 for our numerator. And that doesn't simplify any better. If the 5 and the 6 were to like cancel or reduce, that would be an extra step at the end. But in this case, 5, 6, they don't cancel any. So that's the simplest answer you could put there. Some people, once they get the hang of using technique 3, they sort of backtrack and do the simpler problems that way as well, because it really kind of is conceptually the smallest pieces you can break a problem down into so that it's bite-sized rather than trying to deal with the whole thing all at once. In section 10.5, we're going to talk about an even more complicated situation that goes beyond even this in difficulty level, and it's going to be an entire section of the book devoted to just that one topic. So be prepared. 10.5 is a big one.